All right, hello. Today I want to talk to you about empirical and molecular formulas. This is the second lecture in a unit on percent composition, empirical and molecular formulas. So let's begin today and let's learn about empirical formulas. Let's look at just an operating definition. The empirical formula of a compound gives, and pay real attention to this, the lowest whole number ratio of the atoms or moles in a compound. So what do I want you to take right now? I want you to know that we could be talking about atoms or we could be talking about moles, but if we are talking about the empirical formula, we're going to be looking for the lowest whole number ratio. All right, now you say, well, what do you mean? I say, let's take a made-up compound. So I have a made-up compound. I have X2O10. All right, that is not my lowest whole number ratio. All right, well, how do I know that? Well, because I know that 2 will go into both of these numbers evenly. So honestly, it would be XO5. Now, what is the point? Well, I want you to see the main point right off the bat. This would be the molecular formula because it's giving me my exact number of atoms. This would be what we call the empirical formula, okay? Why? Because it is the lowest whole number ratio. All right? Let's continue. All right? So we can interpret this empirical formula, as we mentioned earlier, we can interpret it at what we call the microscopic, and come on, micro would be small, right? What do I have right here? I have one molecule of carbon dioxide. So I could interpret this empirical formula at the microscopic level, which would be all the way down, in this case, to the molecular level. Or we could look at a mole. Well, why would the mole be the macroscopic? Well, because we know that 1 mole is 6.02 times 10 to the 23rd, Avogadro's number. So we know that that's actually 1 mole is actually a pretty big number, all right? But it has to be a big number because they're so small. But the point is, we can interpret this at the microscopic level, molecular level, at atomic level, or we could interpret it at the mole level, okay? All right, so I want to throw something at you today because I want to make a couple of different points very quickly. So if I told you to grab your periodic table, so you grab your periodic table and very quickly you take a look at it and I tell you that I want you to tell me what would happen between oxygen and hydrogen. Well, you remember your oxidation values, so +1, +2, +3, plus or -4, -3, -2, -1, and 0. So you know that this would have a -2. So it could form an association with 2 hydrogens, which would move it to the octet, and it would create H2O. I'm not telling you anything you don't already know. You learned how to do that the first try when you were studying about bonding. So you say, okay, Mr. Day, so oxygen and hydrogen would come together and form an association and make water. Well, all right, you would be correct. However, you remember that all year long I have said, be very careful about doing your best impression of Moses coming down off Mount Sinai with the 10 Commandments etched in stone. Science is a really big topic. Chemistry is a big topic. There's so much to learn. Be very careful with your rules because there's often an exception to the rule. In this particular case, you would not be wrong to tell me that hydrogen and oxygen would make water. The problem is, or not really a problem, but the interesting fact is that it'll also create hydrogen peroxide. Okay? And you're like, oh, well, I've heard of hydrogen peroxide, Mr. Day. Yes, H2O2 is another association that hydrogen and oxygen will make together. Now, why do you want me to know this, Mr. Day? Well, very simply because I want you to understand that you need to be pretty broad-minded sometimes. Number 2, I want to talk to you today about empirical formulas and molecular formulas. So here's the deal. Water, H2O, and hydrogen peroxide are not going to have the same molecular formula. And quite frankly, they're not going to have the same empirical formula either. Now, before we go any further, I just want you, for interest's sake, to see the sort of the structural appearance of hydrogen peroxide. You got your H2O2, okay? All right, now, read this slide with me. Stick with me. Think. You can do it. Now, if an empirical formula is the lowest whole number ratio, then it may or may not be the same as the molecular formula. For example, H2O2 is really a ratio of 1 to 1. Thus, the empirical formula of H2O2 is really HO. Now think about this, because if H2O2 was the molecular formula of hydrogen peroxide, that's not the lowest whole number ratio. 2 will go into both of these numbers evenly, so really your lowest whole number ratio would just be 1 to 1. Now, that's not going to be the case for H2O. Come on, think about this. You're not going to be able to take H2O any lower than it already is. So H2O is going to have the same empirical formula and the same molecular formula. You need to think about this, and we'll look at it as we go. Okay? Hydrogen peroxide would have a different empirical formula from its molecular formula. Okay, so what is the molecular formula? The molecular formula. Well, the molecular formula gives the actual number of each atom. So hydrogen peroxide is H2O2. That is the molecular formula for hydrogen peroxide. Now, what would its empirical formula be? Well, we've already covered that. We would look for the lowest whole number ratio, and that would actually make it HO, because 2 would go into both of these numbers evenly. Now, what if I had H2O? If I had H2O, then the empirical formula and the molecular formula would be the same, because I would not be able to simplify it any further. For instance, CO2 would be another really good example. CO2 is going to have the same empirical and the same molecular formula. You're going to have a ratio of 1 to 2. 1 carbon for every 2 oxygens. What's the point? The point is that the empirical formula and the molecular formula of CO2 would be exactly the same. Remember, our discussion right now is on empirical, lowest whole number ratio, or molecular, which actually tells you how many you have. In this case, they would be the same. So, what would the empirical formula be for ethene? Well, could you simplify? And the answer is yes, Mr. Day. Obviously, I could take 2 into both numbers, so the empirical formula would be CH. Well, how about if you had styrene? Could you simplify that? Could there be a lower whole number ratio? And you're like, well, Mr. Day, that's easy. 8 will go into both of those, so it'd be CH. Yes. So for these two molecules, the empirical formula would be different from the molecular formula. So understand the difference between the two. Before we even learn to do any problems, understand the difference between the two. Okay? Now, this takes us to a juncture where, and by this point in time, you've figured out that inorganic chemistry is going to have a lot of problems. And so you know that pretty much in every unit, you're going to have to learn how to do some type of problem. So now that you understand the difference between an empirical formula and a molecular formula, then I'm going to introduce you to your first problem. You're going to calculate the empirical formula from percent composition. Now, you've already done percent composition, and you've done percent composition practice problems before you even got to this section, so you know what percent composition is. Essentially, the percent composition tells us the ratio of the masses, which can be changed to the ratio of moles. Remember, all the way back to one of our very first slides, we were either going to look in the empirical formula, we were either going to look at the ratio of atoms, or we were going to look at the ratio of moles. Okay? Number two, after we get the ratio of moles, we will simply reduce it to the lowest whole number ratio, because that will give us our empirical formula. Now, if you need to, go back and look at those again and read them and think about them, but think about what you're doing before you get started in the problems, okay? You're going to be looking for the ratio of moles, and you want to reduce it to its lowest whole number, because that will give you the empirical formula, all right? All right, so here we go. Let's do a problem. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of the compound? Okay, so look at the problem and recognize what you've been given. This is the way you attack every single problem. What have you been given? You've been given percent composition. That's as plain as the nose on our faces. Okay, you have 25.9% and 74.1%. What are you being asked for? You're being asked for the empirical formula. Well, okay, what is 100%? 100% is the whole. So in these particular problems, here's what we're going to do. We're going to assume that if we have 25.9% and 74.1%, then we're going to assume that, or give the value of 25.9 grams to nitrogen. In other words, we're just going to turn that from 25.9%, we're going to turn it to 25.9 grams. Well, how can we do that? Well, because we're taking the parts of the whole, and the whole equals 100, correct? So we're just going to turn this to mass, and we're going to turn this to mass, okay? That much out of 100. So we're going to make 25.9% 25.9 grams, and we're going to make 74.1% 74.1 grams. Okay, now what will that give us? That will give us mass for what we have in our problem, okay? All right, but what do we want to do then? Well, we want to then find the molar mass of each of those items, okay? Because just because we know the mass in the problem doesn't mean that that's equal to the molar mass. It might be more, or it might be less, okay? So we're going to go to our periodic table. You know how to find molar mass, and we're going to look at nitrogen. Remember, nitrogen is the one that we made 25.9 grams. Oxygen was 74.1 grams, okay? So we're going to go, and when we look at the periodic table, we're going to find out that 1 mole of nitrogen has a molar mass of 14.0 grams. You're just taking that straight off the table. You're going to find out that 1 mole of oxygen has a mass of 15.9 grams. Once again, you're taking that straight off the table, and pretty much for the most part, we've been turning this to 16, all right? And I may not have done that in this problem, but go for it. That's what we've pretty much been doing, is turning that to 16. Then we're going to use the line method. What you want on top, what you want to get rid of on the bottom. So what are we going to do? We're going to take our mass of nitrogen from our problem, and we're going to multiply it by 1 mole of nitrogen over 14 grams of nitrogen. Why? Because we want grams of nitrogen to cancel out, and we want our answer to be left in moles. Why? Because you can find the empirical formula if you look at the lowest whole number ratio of moles. Oh, that goes all the way back to the beginning of the presentation when we were talking about how to define empirical formula. Yes. So I'm going to do that, and I'm going to do my math. And you understand that I'm going to multiply, but because this is in the denominator, I'm actually going to divide. So I'm going to divide 25.9 by 14, and I'm going to get 1.85 moles of nitrogen. You have my permission to use a calculator. Check the work, pause, do it on paper, do whatever you have to do in order to be successful and to keep up. What about your oxygen? Well, your oxygen, you had 1 mole at 15.9 grams, or if you made it 16, that's fine with me. And now you're going to do that math. And what are you going to get? You're going to get 1.85 moles of nitrogen here, and you're going to get 4.66 moles of oxygen. Okay, except here's what we said. Now that we know how many moles of each we have, because that's really what we were trying to do, remember? We were just trying to get it into moles. We said that the empirical formula would be the lowest whole number ratio of atoms, or the lowest whole number ratio of moles. So what do we do next? Because really, can we have a lower whole number ratio? Well, what we do next is we take our smallest value and we divide each value by that smallest value, because we're looking to see if we can have a lower whole number ratio. So we're going to take 1.85 moles of nitrogen and we're going to divide by 1.85. We're going to take our 4.66 moles of oxygen and we're going to divide by 1.85. And when we do, we're going to get 1 mole of nitrogen versus 2.51 moles of oxygen. So we're simplifying. But the problem is, and I think you're smart enough to see this, we can't have a 2.51. That's not our lowest whole number. All right? So what are we going to do in order to get our lowest whole number? Well, we're going to do what we need to do to turn this into a whole number. We would have to multiply it by 2, correct? To make it 5. So if we multiply that by 2, we're going to multiply that by 2. Now what do we know? Now we know our empirical formula. We know that our empirical formula would be 2 nitrogens and 5 oxygens, N2O5. That would give us our empirical formula, because the empirical formula is also equal to the lowest whole number ratio of moles. And so that's what we just did in this problem. We found the lowest whole number ratio of moles, which gave us our empirical formula. Now you may need to go back and you may need to look at that and you may need to think about it again and you may need to digest it and you may need to listen to it again. But what we did was we found the lowest whole number ratio of moles, which gave us the empirical formula, because the empirical formula is the lowest whole number ratio of atoms or the lowest whole number ratio of moles. Okay? All right. We're going to close with a little bit of discussion on the molecular formula. All right, so the molecular formula gives us the actual number, which you know. So going back to hydrogen peroxide, the molecular formula would be H2O2. This is how many we actually have. This is not the empirical formula, it is the molecular formula. So, is C2H2, is that a molecular formula or is that a empirical formula? And you're like, well, that's easy, Mr. Day, because it could be simplified, so it has to be the molecular formula. Very good. C6H6 or benzene, is that a molecular formula or is it an empirical formula? And you're like, well, that's easy, Mr. Day, because it could be simplified, so it has to be the molecular formula. Yes. Now, if you simplify it, right, go to that lowest whole number ratio, then you turn it into an empirical formula. But right now, those are both molecular formulas. Now, what would the empirical formula be? It'd be CH. It'd be CH. Is this an empirical formula or a molecular formula? Well, you're like, well, I can't simplify it any further, right? So what's your educated guess? Well, your educated guess is going to become that it is an empirical formula. Now, I suppose that it is possible that I could throw something at you like CO2, right? And you would have to say, well, it's both. So it's within the realm of possibility, but when you see something that cannot be simplified any further, you know, you're pretty much going to be thinking empirical most of the time, I would say. Okay? All right. The molecular formula is either the same as the empirical formula or it is a multiple of the empirical formula. Remember, the empirical formula has been simplified. The molecular formula is how many you actually have. Okay, so in hydrogen peroxide, your empirical formula is HO, but your actual molecular formula is H2O2. All right, you can calculate, and this is the last problem that we'll look at. You can calculate the molecular formula from the empirical formula, okay, if you know the compound's molar mass. So, find the molecular formula of a compound whose molar mass is 60.0 grams per mole. And its empirical formula is CH4N. Okay, so once again, what do? The very first thing, you recognize what you've been given. What have you been given? You've been given the molar mass, and you've been given the empirical formula. What are you being asked for? You're being asked for the molecular formula. Okay? So what are you going to do? Well, you're going to start by calculating the empirical formula mass. The empirical formula mass. In the problem, you were told that it was CH4N. So what are you going to do? You're going to go to your periodic table, and you're going to do your math. You're going to come up with 1 times 12, 4 times 1, and 1 times 14. This is stuff that you already know how to do. It's simply molar mass. Okay? You're going to add these things together. All right? And when you do, you're going to find that your answer is 30 grams per mole. So the empirical formula mass, so this right here, the empirical formula, is equal to 30.0 grams per mole. All right? Now, once you have that piece of information, what are you going to do? You're going to go to your second step. You're going to divide your molar mass, which you were given in the problem, by the empirical formula mass, which is what you just calculated. Now, your grams per mole is essentially going to cancel out, correct? 60 divided by 30 is going to be 2. Oh, so now I have my multiplier. Yes, now you have your multiplier. And what will you do with this multiplier? You'll multiply it through the empirical formula, which, as you recall, was CH4N. So what if I multiply that by 2? Then I would have 2 of those. What if I multiply that by 2? Then I would have 8. What if I multiplied that by 2? Then I would have 2. What is my molecular formula? C2H8N2. All right, if you need to go back, watch again, rewind, think, look, pause, do what you got to do. Take the time that you have to take to wrap your mind around it. Nobody's going to wrap their mind around everything right off the bat, and it will require thinking, and it will require some effort. The empirical formula is the lowest whole number ratio. The molecular formula is how many you actually have, okay? And then we learned how to do 2 problem sets. So make sure you understand how to do the 2 problem sets in this particular lecture. All right.